This is part 2 of a simple introduction to CometBFT. If you haven't yet, check out the first video which introduces CometBFT and replicated state machines. This video focuses on the application blockchain interface used by CometBFT. Today we're going to explain what ABCI is, we'll explain what some of the messages are, and we're going to discuss the ABCI++ variant. So let's get started with an introduction to ABCI, the application blockchain interface. ABCI is the interface between CometBFT, which recall is the state machine replication engine, and your application, which defines the state machine that's being replicated. ABCI is a programming language agnostic communication standard, which is defined as a set of protocol buffers or protobufs. These protobufs specify the request and response types exchanged between CometBFT and the application. So the conceptual model is that CometBFT acts as the client and your application acts as the server. CometBFT will send different ABCI request types, and the job of your application is to generate the appropriate responses. Now, you can run both CometBFT and your application in the same process. So if you use the Cosmos SDK, which is written in Go, you'll be running them in the same process. You can also run CometBFT and your application in separate processes. So maybe you want to write your application in Rust and you want to run the Golang CometBFT implementation as a standalone binary. You can do that too. So either approach works. So let's take a look at some of the most important specific messages in ABCI. So first, this is how block and transaction execution works in ABCI. So first, I want to note that this is before ABCI++, which we'll get to shortly. So this is relevant for CometBFT versions 0.37 and below. So the 3.7 release series. So first, CometBFT will send a BeginBlock message, and that includes the block header and related metadata. Then for every transaction, there will be a DeliverTx message. So there's one DeliverTx per transaction to be executed. So the application executes each transaction, updates its internal state, and then finally, once all the transactions have been delivered, then EndBlock, the response, will return the new app hash. So the app hash is just a cryptographic hash that is a succinct representation of the application state, and that's included in block headers. So finally, in step 4, we commit. So CometBFT sends the commit message, and at that point, the application must persist its state changes for the block. The application's internal state via the app hash becomes canonical, and at this point, block execution is completed. So the cool part about this ABCI approach is that each one of these messages that CometBFT is sending, it acts as a hook where the application can run custom logic at specific points in the block lifecycle. So if we have special processing, for example, that we want to do at the end of the block, we can put that logic in the handler for the EndBlock message in our application. So we've discussed what happens when a block is being executed. So before that, there's the mempool. So the mempool is just a node local in-memory pool of uncommitted transactions. So these transactions are eligible for inclusion in future blocks, but have not yet been included. So nodes gossip mempool transactions to one another. When a node becomes a proposer, it's going to pull transactions from the mempool to populate its proposed block. So whenever a node receives a transaction, either directly from a client or via gossip, CometBFT sends a CheckTx message to the application. And that application then needs to decide whether the transaction should be accepted into the mempool. And so this is a place where we can have the application perform lightweight validation. So fast, mostly stateless checks, and possibly inexpensive stateful checks. And the CheckTx response is going to tell Comet whether or not the transaction should be included in the mempool. Now, CheckTx is intentionally limited because there's a denial of service vector. So Any expensive validation done here is going to slow gossip, for example. And from a security standpoint, that's fine. We're going to do full validation during DeliverTx if the transaction later gets included in a block. And also importantly, CheckTx is not going to modify or commit application state. It's really just an optimization to filter out gossiping invalid transactions. Okay, so next we have, let's take a look at how an ABCI application bootstraps. So the first start of the chain from Genesis, CometBFT sends an init chain message. So this happens exactly once for a fresh application instance, and CometBFT will pass in the initial state that's defined in the Genesis file for the application, and the application can use that to initialize its initial state and return an app hash. After that, and on every subsequent CometBFT restart, CometBFT is going to send an info message, and that's basically doing a handshake between CometBFT and the application. The application has to report its last committed height and app hash, so CometBFT can make sure that both sides agree on the current state before continuing on. Now let's take a look at ABCI++. So these are major changes that were recently introduced. And they were introduced incrementally across the 037 and 038 CometBFT release series. So let's take a look at those. So the first set of changes were included in the 037 release series. And the basic idea here was to give the application more control during the proposal phase of consensus. So that's the part of consensus where a block is being constructed and evaluated prior to votes being cast. So the two most important hooks are PrepareProposal and ProcessProposal. So PrepareProposal is only used for the proposer. The proposer is the validator that's selected for a given round to assemble transactions into a block and propose that block to the rest of the network for consensus. So instead of CometBFT just blindly pulling transactions from the mempool, the application will get to decide which transactions go into the block and in what order. Then ProcessProposal is called on all validators when they receive a proposed block. So that's a place now where the application can validate the proposal as a whole and either accept it or reject it before voting. So the application is no longer limited with these two changes to doing the transaction by transaction checks. With ABCI++, it can now enforce these block level policies. So things like ordering rules directly in the consensus flow. In addition to the proposal time hooks, ABCI++ also introduced changes around voting and block execution, which landed in 038, version 038 release series. And so the first change is vote extensions. So with vote extensions, validators can attach additional application-defined data to their consensus votes. So extend votes is called when a validator is about to cast its vote. That lets the application add some data. So they may do a little bit of computation based on perhaps local state or the proposed block and include that as part of the vote. Other validators can then use verify vote extension to check the additional data is valid. And those are application defined rules before accepting a vote. So that enables new classes of protocols, so like doing threshold signing, DKG, stuff like that, or distributed key generation. The second major change is the FinalizeBlock message. So in earlier versions of ABCI, as we saw, block execution was split across a bunch of different messages. BeginBlock, a series of DeliverTx messages, one for each transaction, and then EndBlock. In 038, these are combined into a single FinalizeBlock call, and the commit is still there, but as a separate message. And so the advantage of that is it just makes block execution more explicit and atomic. The application gets the full block at once, executes it, returns the final app hash, and execution results in one step. So it's still worth knowing the earlier ABCI approach because a lot of changes are still using it. But overall, these changes simplify the execution model. So Today we learned a little bit about ABCI, how block execution, the mempool, and Genesis works. We also discussed the major new changes introduced in ABCI++, specifically giving more control to the application over the proposal phase, adding vote extensions, and simplifying the block execution model. So that was a simple introduction to CometBFT and ABCI. I hope this was useful, and thank you for watching.